Alright guys, today we're going to be talking about disk method. And to talk about the disk method, we're going to start with any old function. So let's go, just make it look something like this. And we're going to take that function from A to B. And what we're going to try to do is we're going to try to take this function, we're going to take the area under the curve here, whatever the area ends up being, and we're going to wrap it around the x-axis. So we end up getting this mirrored thing here brought down around the x-axis. And actually this will look kind of like a vase maybe on its side if you were to wrap it around the x-axis. Now, some people have a very easy time visualizing what this will look like when it gets wrapped around the axis, and some people will not. If you can visualize it, this chapter is going to be so much easier for you because we're going to do a lot of things that's called revolving, revolutions around different axes, either around the x-axis or eventually around the y-axis. Now today we're really only going to be looking at most of them around the x-axis. So taking any of the rectangles, revolving around them, and trying to get an actual volume that this picture kind of represents. So what we're going to do is we're going to take our representative rectangle right here. It's going to have a height of whatever the function is. So our function height is f of x. And it's going to have, so that's our f of x height. When we wrap it around, if you turn it on its side, it ends up making a disk. So if we were to take this sideways, look at a cross section, this would be our f of x, be our rectangle. But when we wrap it around the axis, we're looking at this sideways on, this is the axis right here, we end up making a disk. And the area of a disk is just, well, pi r squared. And each of these radius is the function height. And if we're going to take one rectangle, add in the next rectangle, add in the next rectangle, and so on and so forth, and each little rectangle is going to have a really small width. And this width is our dx. So to add them all up, add up all of our change, we really want to end up doing the integral. So our formula then becomes the integral of pi, which is a constant, r squared dx times a little width. Well, r squared, we just said, was our function height. So our formula really works out to being pi integral f of x squared dx. And generally they're going to give us the bounds from a to b. So it's pi r squared, area of a circle, integrated on our bounds. So let's take a look at what that looks like a little bit more visually. So I'm going to jump over here. And I think I'm still recording. That's what happened in my one video, is I thought I wasn't recording, but I really was. So I'm hoping this still is recording. So we've got this function with our slope here coming down and our representative rectangle. If we go to revolve our representative rectangle around, we end up seeing that it's making this disk shape. That's really what's going on here. Our function height is our radius of the circle that's coming around here, and our dx is our width of the rectangle. Now, if I wasn't going to just revolve the one, if I wanted to revolve the entire region, this is the overall shape that we're making. And we're trying to find the volume of a solid that kind of looks like this in general. So to find it, we take each individual rectangle, revolve them around, and then we've got it. And I'm hoping that recorded all that stuff in between there. We'll see what happens.